Hello students, how are you all? Fine. And today we will learn about data representation and memory storage devices we have learned in last video.
Now, introduction. We are familiar with number system in routine daily life. Decimal number system is a positional number system. 10 symbols are used. Say 0 to 9, it is a 10. It is used in a daily life. We use alphabet A to Z also. Besides this, we use special characters all over available on the keyboard. Okay, now all languages are used for communicative purpose. See, this is the only number system used in electronic media actually, and digitally we can say that is a use for communicative purpose. Computer is not understand these human languages. You all know that computer is an electronic machine. It doesn't understand human languages. Say it only understands zeros and ones. What? Zeros and ones. That two states on and off. See, one for on and zero for off. So the bi-state language having two symbols, that is on and off, I already mentioned. So the binary number system that can represent binary in the sense that is a two numbers itself is a binary numbers. Now binary number system. Binary number system has two symbols, that is 0 and 1. You already know. A single digit is called bit. For example 1, 0 or 1 say. Okay. Now these representation use suffix 2. Why it is suffix 2 by conversion? Because binary digits are 2 actually. Now binary number system represented 101B or say 101B. That is, it doesn't matter capital or small, but it is stands for binary numbers. 101 number represented say 101D or say 101D, small and capital, then 10. 10 also stands for decimal numbers. Now positional numbers is like unit, tens, hundreds. You have already learned this number in a say primary section, but here positional number will go right to left, starts from 0. Same binary number system, there is a positional number. Positional number we will give right to left. Now binary number can converted into the decimal number using this method. We will use this method and convert the binary numbers into decimal numbers. So here we will convert 101, base is a 2. So in a decimal number like this, say 1, this is a we have taken 1, then multiply by 2 because its suffix radix is 2. Now here we'll give 2. Now this is a position number, then again we'll take 0, then multiply, then 2, and position number is 1 from right to left. Okay, now here 1 is given last here, that is right to left. Here will be radix will be 0 and the suffix is 2. So it when we convert in this decimal number, manipulate this number, we will get for this calculation we will get 4. From this calculation we will get 0. Calculation here, that is we will get 1 instead of position number 0, but here it is a 1, we will take the 1. So answer will come 5. So 101 in a decimal say number is 5. Okay. Now a binary number system having base 2, that is we have already discussed in a previous slide, and say decimal number having base 10, because it is a 0 to 9, it is a 10. Now here is the first method we will apply. Suppose we will convert some number, say suppose 44 we have converting number in a binary. So whenever we take the base 2, so if we multiply 2 into 5 times, we will get 32. Okay, this is the first step. Now subtract 32 from 44, we will get 12. Now again we will convert, give power to 4. So how many digits we will get? 16. 16 is not subtracted in a 12, so binary number comes 0. Okay, now remainder 12. Now so 12 is less than 16, so when it is subtracted, then binary numbers will come 1. Okay, so hence it is not possible to subtraction yield a positive number or say 0 non-negative, we can choose power 3. Okay, because it is not subtractable, then we will take instead of 4 we will take 3. Now which is 8, so now 12 minus 8, it is possible, so we will get the number 8. So last remainder is a get non-negative number. Figure 4.9 complete calculation we will see on the next slide. Now 44 we have converting binary numbers. So when we 2 raised to 5, that is a 32. 32 is a subtract in the 44, we will get positive numbers. So it means that we will place here 1. Okay. Now here when 2 is raised for 4 numbers, say it will not subtract by 12. So 12 minus 16 is not possible, so what binary digits will come here? 0. Now here comes again the next step. Now 12 is minus 8, because 2 raised to 3 is equal to 8, so we will get the remainder, positive remainder. It means that here will be say 1. Now again come here 4, 2 to the 4, it is a subtractable, yes it is subtractable, so we will get 1. So next is a say again we will position number will get say 2, then a power 1, so we will get 2. 2 is not subtractable from 0, then we will put here 0. Now again 2 raised to say 0, we will get 1, but it is not subtractable from the say 0. Okay, so it will comes negative number, so we will get the binary number digits of 44, say 1 0 1 1 0 0. Okay, again we will take the second method of converting binary numbers into the decimal numbers, and this is called divisional method. 125 base is 10, because this is a decimal number. How much is a base 10? It means that how much it will be binary numbers. So what we will do that, say here 125 continuously divide by 2, because base is 2. So we will get, if we get the remainder 1, say here will be 0, then here is not say divisible, so we will put again 1. Here is this is 0, we will take 1, and we will write it in a bottom to top. So we will get the conversion of 125 base 10 of decimal numbers in a binary numbers of 125 conversion. Unsigned integer number representation. Unsigned integer number 0 or positive numbers represented in a converting into number into equivalent binary numbers. How it can possible? Let us check again. We will take again the representation. It is a represent 8 bits actually. Unsigned integer, it's represent 8 bits actually. Okay. Now again we will take 1 0 1. This is a second position, this is a first position, this is a 0th position, this is a say we can say right to left. So place value we have already put, and here we will get the decimal number value here. So how can represent this 8 bits? Because we have got 101 is already there, 3 numbers are there, so we will put say prefix 5 zeros to complete this 8 bits. Okay, positive numbers. This is unsigned integer representation. Now binary number system again. Here we will again take the positive numbers, and here it is a chart of say 0 base 2 and 0, it will 0 in the decimal numbers, so on. And here we will check that when we will convert this binary numbers into the decimal numbers, we will get 27 base 10. So these all exercise you have to do at home. Okay, now addition, subtraction, etc. can be done, but cannot store the negative numbers. See, in unsigned integers representation, we will only store the positive numbers, not negative numbers. So to store negative numbers in a 2's complement method, we have already learned 2's complement method in a 7th standard, say 1's complement method and 2's complement method. So how it can be used in a conversion of this say binary to decimal and decimal to binary. Sign integer method to represent 0, positive, negative, whole say number representation. Three schemes, there are three schemes that is used to represent sign integer method. One is a sign magnitude, second is a 1's complement method, and second is a 2's complement method. Sign magnitude method. In this method, prefix 0 for indicating positive number and 1 is used for negative number. It means that if any binary digits having prefix 0 or 1, that indicates 0 for positive number and 1 for negative number. Let's convert say -5 base 10 into the binary numbers. So to store into the memory, first convert it into the equivalent binary numbers. First we convert it to in a say binary numbers. Then first bit is 1, so it is already indicate that it is a negative number, and remaining bits are binary digits representing the number. Next is a binary numbers representing this number, so which is equivalent to say 101 base 2. Now it has limitation, say 0 can represent both the positive and negative numbers. 1's complement method. In binary, 1's complement method refers to converting binary numbers say ones into the zeros and vice versa. Okay, it means that 0 represented 8 zeros is a plus 0 and 8 ones it is a plus 1. Okay, we have already discussed in a say unsigned integer and positive integer, that is a 8 bits are there. Now but in a 2's complement method is very popular, all the significant bits are taken. Okay, now example on the next slide. 2's complement method. Here is a given number of binaries, that is a 2's complement method. We convert it in a decimal numbers. How can it possible? Suppose we are converting this one. So this is a multiplication method that comes 8 in a decimal numbers. Now check it out, the last number here, the first digit is comes 1. So what it represent, that we have already converted, but we will get the -9 base 10, because the rest of the we will say this is a binary representation and this is a representing -1, so it is a -9. Use this method. Table showing 2's complement method conversion, this table is showing. Now considering binary numbers into decimal numbers, binary numbers into decimal numbers, and invert binary zeros to ones and vice versa, and add 1 at the last, adding 1 in a after all the calculation in a say subtraction method, that is a 2's complement. Now 2's complement method, sign integer, it is represented like this, -1 raised to n minus 1 and plus n minus 1 then -1. It is say how can it represent binary digits 8, 16 and 32, and minimum numbers we can combination of minus say 2 raised to 7 is a -128, and plus 2 raised to 7 it is a -1, it is a plus 127. So it 8 bits from -128 to plus 127. This is a maximum number, this is a minimum number. Now 16 we can say -2 raised to 15 because here it is 16, we will start from 0, it will be 15, and here is also start from 0 to 8, that is a 7. Now minus 32,768 to plus 32,767, that is a 768 minus 1. Okay, now 32 bits. Now this much store can be, now operating system also working on this 32 bits. Now how can it will take minus 2 raised to 2 is a binary digits, and 31 it represent minus this amount 2 plus this amount. It is a range of numbers, so it means that computer can store 32 bits, computer store minus this amount to plus this amount in a range. Okay, floating point number representation. To representing fractional number, floating point numbers representation is used. It means that if we write suppose 263.3, this is a call say fractional number, because it is a say comes in a decimal. Okay, now the IEEE, that is a 32-bit single precision method commonly used to represent real number. Okay, real number always comes in a say in a decimals. Okay, now here Institute of Electrical and Electronics Engineer, this is a full form of IEEE. Now the world's largest professional association for advanced technological innovation and excellence, this is totally all the institute are using this method for converting binary numbers into the say decimal number in a floating point. Floating point means what? Fractional number. Floating point number representation, three parts are given. Say most significant bit is a sign bit, that is represented by S. You look at here, and with 0 for negative numbers and 1 for positive numbers. Okay, now 8-bit represent exponent. You look at this part of the this tabular form, that is an exponent represented by E, denoted by E. Now 23 bits represent fractional part. See, here is a fractional part, 23 bit 0 to 22, that is a 23 represent the fractional part. Now floating point number representation, sign bit represent sign of the numbers. Say whatever numbers are in a binary numbers, if it is a fractional number is positive, it is represented by 0, and 1 is a negative number. You check it out with me here. Say here 1 is a, you check, 1 is a single bit sign, that is a 1, it is a negative number, and here 8 bits exponent, it is here, and fractional this 23 numbers, it is a fractional in the 23 bit. Exponent is say this binary numbers. Decimal equivalent to this number is 129. Say we can say it is a 129D also, that is a D for decimal number. In normal form, actual exponent is E minus 127, exponent minus 127. We have already learned in the say in a tabulars. Okay, that is a 8 bits minus 1, it is a comes 127. Okay, 127 it is a comes in 8 bit. So 129, that is a here conversion of this one, 129 minus 127 is equivalent to 2D. It means 2 decimal numbers. So here again this tabular form is given same. You just check it out with. Floating point number representation is always for fractional part actually. So here we will consider another example. Just look at this binary number. So sign bit as 1 indicates for negative, we already discussed, and if the here it is a 0, it means that this is a negative number. So exponent this break this part into 2, say binary, it is equivalent to say 126 decimal number, that is we convert in a multiplication method. Okay, so the fractional is 1.1 binary, say with an implicit leading 1. So 1 indicating that it is a say negative number. So 1 plus 2 power 2 minus 1, that is a 1.5d, that is a decimal number. So the number is minus 1.5 binary numbers, power 2 power to 126 minus 127, that is a minus 0.75 decimal. So 0.75 is negative number because here it is a indicating 0. Now character representation. Character also represented in bit patterns, that is a group of say 7, 8, 16, 32 and so on. Rules that determines the bit pattern specific length are known as a coding scheme. See, bit patterns are called coding scheme. 7-bit American Standard Code for Information Interchange, that is called ASCII character, and 8 bits American National Standard Institute ANSI code, and extended binary coded decimal interchange code, that is a EBCDIC were used. Now here is some representation of the symbols. Say 7 decimal number place is a 55, then greater than 62 place in a decimal, and capital letter A is placed on 65 in ASCII characters, that we already discussed in a 7th standard. Unicode character representation. One can represent maximum 256 possible pattern using size of 8 bits. Okay, we will discuss afterwards this one. Unicode scheme represent characters in a computer memory, just like ABCD, capital letter, special character, and all the things are represented in a Unicode scheme. Unicode developed by Unicode Consortium, that is you can visit this site, you will get. It is compatible with schemes like ASCII. It is a familiar with ASCII character also, so both are working same. Okay, now Unicode represent character use 16 or 32 bits. Always you can find the PC OS by 16 or 32 bits. Okay, now capable to all languages across the world. In this bit size, computer can handle all the languages which is spoken across the world. 16-bit Unicode allows 65,536, that is a 64K patterns, and 65,536 unique characters also. 44,900 character more added in a May 2001 latest standard of 32 bits. 1 lakh character patterns actually. Unicode character representation, you just this is a Unicode and it is a character representation, same is the like that description here given here in this table. Now image representation. Image representation in a computer is called digital image, and image is a sequence of zeros and one in a computer memory. Image can be described contains using position and size of the geometric forms and shapes, just like you are watching this screen also. Here is a different size shape, here is a different size shape, that can be geometric shapes and forms and position that described like an image as lines, curves, rectangles and circles. Okay, now such representation is called vector image. Just like you watch it, this here is a big arrow, here is the same small arrow, this is all called vector image actually. Vector image can shrink without affecting the quality. See, if you reduce the picture on the screen, it cannot affect the say in a quality, okay, clarity. Another way to represent image in a fixed row and column. Sometimes it is a in a fixed row and column. Okay, each row and column intersection is known as a pixel. Wherever the rows and column intersect, that is called pixels, picture cells actually. Okay, more row and column increase quality of the picture. If you use more rows and columns, say pixels, that is increase the quality of the picture you have already seen in your mobile device and all computer. Now set pixels in the form of two-dimensional array. If an image pixels are 2048 width and 1536 height, so we have to multiply both the numbers, we will get 31,45,728. So it is a pixel of that picture, or say we can say equivalent to 3.1 megapixel. Okay, that is called in a short form MP. That is familiar with you when you use the mobile camera, it is always denoting the MPs. Okay, that is called megapixel. Mobile camera is also having MP say size of 48, 64, 70, etc. Now 2048 and 1536 also called a resolution of the image. Suppose this pixel is given, that pixel combined with each other, that is called resolution of the image. More resolution, more clarity of the image, more quality of the image. Resolution always count the terms of pixel. This resolution always count in a pixels. More the pixel, more the clarity in the picture. To avoid memory management and image transferring problem, so the images can be stored in a compressed form. Here it is given compressed form, that is .bmp bitmap image, .jpg joint photographic expert group, .png portable network graphics, .gif graphics interchange format that you are using for animation, .tiff tagged image file format. These are all say a compressed form of image. Other media representation, just like images, audio and video also represented in digital information. Okay, the sound audio file have formats like dot wave, waveform, audio file format, dot mp3, moving picture expert group, and also WMA, that is a Windows Media Audio, are very popular. Now about video files, in a second more than 45 frames moving. Okay, whenever you watching this video, in this video also in a 1 second 45 frames are moving. That's why it is a coming video format. Okay, generate effect. The popular video formats are .flv, flash video, and AVI, audio video interleave, .wmv, that is a Windows Media Video, .mp4 moving picture expert group format. Okay, these are all say digital information. Students, chapter 4 is over. Hope you like this. Any feedback, queries and suggestion regarding this, please message me, contact me. Thanks for watching. Thank you so much.